Welcome to Homework Lib.
Question.
Understanding inductance in an RL circuit through exponential current growth. In electrical engineering, analyzing how current behaves in circuits composed of resistors, R, and inductors, L, is crucial for designing reliable, safe, and efficient systems. An RL circuit, one containing a resistor and an inductor in series, offers insight into how current changes over time when a voltage source is applied. The resistor opposes the flow of current by converting electrical energy into heat, whereas the inductor opposes sudden changes in current by generating a countervoltage, EMF, which is proportional to the rate of change of current through it. The nature of RL circuits. An RL circuit does not respond to a voltage source instantly. When the switch is closed and voltage is applied, current does not jump directly to its maximum possible value. This is due to the property of inductance. Inductors resist changes in current flow. Initially, the inductor creates a back electromotive force, EMF, that opposes the incoming current. Over time, as the magnetic field around the coil builds up, the rate of change of current decreases and the back EMF falls. Eventually, the current settles at a final steady-state value determined by the resistance in the circuit, as if the inductor becomes a simple connecting wire. How does the current rise? The rise in current follows an exponential curve described mathematically by IT equals I text left 1 minus E frac RL t. This equation tells us how the current increases from 0 toward its maximum value, I text max over time, T, depending on both the resistance R and inductance L. The term tau equals frac LR is called the time constant of the circuit. It characterizes how fast or slow the current approaches its maximum value. After one time constant, T tau, the current reaches about 63% of its final value. After two time constants, it reaches about 86%. After 5 time constants, it's more than 99% of the final value. This predictable rise is key in systems where a controlled buildup of current is necessary, such as in transformers, radio transmitters, motor drives, and various signal processing circuits. Purpose of this experiment. This experiment seeks to determine the inductance, L, of a coil based on how the current increases over time. Instead of using physical instruments to directly measure inductance, which may be expensive or unavailable, we extract it from the exponential nature of the current curve. Given data from the experiment, resistance of the coil, R equals 8.5 omega, applied voltage EMF, E equals 80.75 T. Initial condition, switch is closed at T equals 0. From the current time graph, IT equals 4S equals 5.0 text A. Final current can be computed as I text max equals frac E equal frac 80.75, 8.5, 9.5 text A. The mathematical model used. The equation IT equals max left 1 minus E vac R LT right, where IT equals current at time T, I equals maximum current after a long time, R equals resistance of the coil, L equals inductance to be determined. T equals time in seconds. We will now substitute the known values to solve for the unknown inductance, L. Step-by-step calculations. Step 1, plug values into the exponential current formula. From the graph, at T equals 4S, the current is 5.0 A. I text max equals 9.5. 5.0 equal 9.5, left 1 NS E frac 4R right. Step 2, divide both sides by 9.5. Frac 5.0 and 9.5 equals 1 minus E frac 4R LL. Right arrow 0.5263 equals 1 minus E minus frac 4RL. This isolates the exponential term. Step 3, rearranging E4RL equals 1 minus 0.5263 equals 0.4737. Step 4, take the natural logarithm of both sides, minus frac 4RL equals 0.4737. Substituting R equals 8.5 omega, frac 4 times 8.5 L of 0.737, right arrow minus frac 34.0 L, equals 9 to 0.747. Step 5, solve for AC 34.0, L equals 0.747. Right arrow L, frac 34.0.747 approx, boxed 45.5 text H. Final result. Therefore, the inductance of the coil is boxed L approx 45.5 cm. Interpretation of the result. This is a very large inductance. Inductors of this size are typically found in large industrial electromagnets, heavy-duty transformers, power conditioning equipment, pulse shaping circuits in laboratories. Why is the value so high? Because the current takes longer to reach its maximum. It implies a higher inductance, more opposition to change. This is beneficial in situations where smooth current transitions are needed to avoid sparks or surges. Stable magnetic fields are required, e.g. MRI machines, particle accelerators. Inductive energy needs to be stored temporarily in switching circuits. Real-world relevance. This method of determining inductance from a voltage-current-time relationship is common in both academic and professional electrical engineering practice. Instead of relying on expensive LCR meters or disassembling devices, engineers can take a few key measurements and apply this exponential growth model. Applications: checking for damaged or degraded inductors in motors, designing relay timing circuits, tuning radio frequencies, measuring solenoid behavior, calculating coil parameters in transformers. Because exponential growth and decay are common in all first-order systems, not just RL circuits, but also RC and thermal systems, mastering these equations provides deep insight into dynamic electrical behaviors. Summary table: parameter, value, current, resistance R, 8.5 ohms, voltage EMF E, 80.75 volts, final current, I text max 9.5 A, current at T equals 4S 5.0 A, inductance L 45.5 H, time constants LR 5.35. Educational insight. This example illustrates a foundational principle in electrical circuits. It connects theory, differential equations, exponential functions, with tangible experimental procedures. It also introduces engineers and students to the practical application of Kirchhoff's laws, Ohm's law, exponential time-dependent analysis, logarithmic solving techniques, extended learning opportunities. Want to go further? Here are some suggestions to build upon this concept. 1. Varying R or L. Change the resistance or inductance and observe how time constant and current growth are affected. 2. Using RC circuits, replace the inductor with a capacitor and analyze charging behavior. The math is similar, but the physical meaning changes. 3. AC circuit behavior. In AC circuits, inductors resist change in current through reactance, XL equals 2 pi FL. Compare this with the DC analysis. 4. Energy storage in inductors. Compute energy stored, E frac 2 Li squared. 5. Magnetic field calculations. Explore how inductance relates to physical coil design. L equals Fresnel QA L, where N is number of turns, A is area, and L is length of coil. Conclusion. This detailed study of current growth in an RL circuit highlights how engineers can derive the inductance of a coil using just a few accessible measurements and a reliable exponential model. The result of L approx 45.5 text H demonstrates not only the physical behavior of inductors in circuits, but also the effectiveness of mathematical tools in solving real-world electrical problems. Understanding how current grows, how inductance resists changes, and how these properties affect circuit design allows engineers to make informed choices in everything from delicate instrumentation to heavy-duty industrial machines. This is more than just a calculation. It's a window into the invisible world of electromagnetism that underpins modern electrical engineering.